All right, so today we have Ronald Hill is here, I guess here in Princeton, but he's originally from Tel Aviv. And he'll tell us about discrete probability statistics, physics stuff.
Right. So thank you, Avi, for inviting me to this seminar. Thank you all for coming. So I'd like to interest you in some ideas about geodesics and minimal surfaces in a random environment. The talk will emphasize many open problems, and I think many of them are of combinatorial nature. So I hope that you will be interested, maybe think about them. There are, I think, important problems. I hope progress can be made. So, and of course, some results as well. So we will talk about geodesics and minimal surfaces. Actually, this talk is a combination of 3 talks, but hopefully that will go well. So there are joint works with Barbara Dembin, Dor Elboim, and Dor Elboim, and then there are joint work with Michal Bassan and Shoni Gilboa, and another joint work with Barbara Dembin, Dor Elboim, and Daniel Adas. We will see as we go, but I hope it will not be too confusing. Here are some pictures just to have an idea. We're going to study random paths. So these will be minimal paths in a random environment, as will be defined in a second. It could be in a higher dimensional space. So this is a path in 2 dimensions, and this is a path in 3 dimensions. Throughout, sometimes I will use these notations. D is the dimension of the path itself, which is 1, and n is the codimension. If you have a path in 3 dimensions, then the codimension is 2. And here you have a 2-dimensional surface in a 3-dimensional space. So the dimension of the surface is 2 and the codimension is 1. So we will get to that. Okay, so let me start. The first thing I'd like to tell you about is first passage percolation. So this is the idea of a minimal path in a random environment based on joint works with Barbara Dembin and Dor Elboim. There are some pictures of that here. Let me start with explaining what that is about. It's very intuitive. The idea is that you have Euclidean geometry in RD or in ZD, as we will actually do. And we're going to make random perturbations to it, which are localized, so kind of independent, small local perturbations. That's the idea. And and then we're going to study the new geometry that is obtained after these perturbations. So how is that actually going to go? It's going to go as simple as this. So we're going to take the ZD lattice, and to each edge of the ZD lattice, we're going to give a weight. The weights will be independent and identically distributed. What is important is that they are non-negative. So it is the capacity or the length of it, or the length or the energy of an edge, as you prefer to think about it. What is important is that they are non-negative. And in this talk, they will be, as I said, IID, and also supported on some compact intervals. Say they are uniform on 1, 2, so absolutely continuous, uniform in positive density. The picture also has weights which are less than 1 or more than 2, but you could choose other weight distributions. And the passage time between 2 vertices. Okay, so what happens when you endow the ZD lattice with capacities or weights or lengths? Well, it turns the ZD lattice into a random metric space. In what way does it turn it into a random metric space? Well, if you now fix 2 vertices, U and V, you can ask, what is the shortest path between them? Shortest means that the sum of the edge weights along the edges of that path is minimal among all paths that connect these 2 points. Unlike in the picture, there is no restriction that the path goes back. So if these are the 2 points, then maybe the minimal path looks like this. There's no restriction over that. So long as the sum over all the edges in the path is minimal among all the other paths. And then you can discuss the length of that path, that's TUV, and you can discuss the path itself, that's gamma UV. You can easily convince yourself that when the distribution of the weights is absolutely continuous, there is a unique such path. Existence and uniqueness are guaranteed. So we may speak about the path, which is called the geodesic, and the length, which is always well defined. So now we have a random metric space, and this is what I meant when I said that we have a minimal path in a random environment. And we're going to try and understand it. We're going to try to understand the large-scale properties of this metric, in particular to understand long geodesics. For instance, here is a simple question. You take two faraway points. You might expect that on a rough scale, looking very far away, the path between them, the geodesic, is kind of flat. So how flat is it? So you may draw the straight line and try to measure the deviations from the straight line. That will be a question that will be very important to us in this talk, one of the fundamental issues. And since this is a discrete math seminar, you may ask yourself, why do it on the ZD lattice? Why not do it on other graphs? And indeed, you may do it on other graphs. The complete graph was investigated by Jansson and more recently by Remco van der Hofstede and co-authors. Hyperbolic settings were investigated by Bignamini and Tessera. The hypercube was investigated by Aldous and Phil. And on trees, it's related to branching random walk. So indeed, people do it on other graphs. But I come from a statistical physics motivation where the main focus is always on ZD or RD. And you may imagine that this actually has some bearing on reality. Maybe you're a drone for Amazon and you want to go from the one point to another to deliver a package. What is the minimal path that you should choose? And it's not exactly a random environment, but maybe you can compare it to if the environment was random, how much longer it is than you would expect under random circumstances, could give a benchmark. So you could imagine that ZD is also interesting, or RD. Okay, so this is our goal for the first part of the talk. We will talk about minimal paths in a random environment. Later, minimal surfaces. And for those coming in just now, I will say very briefly, each edge is given a random weight, and then we try to find the path of minimal sum of weights between 2 points and investigate that between very far away points. IID weights, uniform 1, 2. Okay. So what is predicted about this model? Well, now I will do some physics slides. So I will explain what is expected, usually by physicists, but not what is proved, and very little is proved. I want to emphasize the open problem. Okay, so here are some basic, this slide, I changed it a bit and all the appear animations went bad, I see. So, basic predictions concern the passage time. So you should have in mind something like law of large numbers. So you should have in mind things like we are used to from basic probability. Law of large numbers, fluctuations. Then you could try and go further to CLT or something like that, and so on and so forth. So what does it mean, law of large numbers? Well, I have 0 here, and this endpoint vertex, I'll call it L times V. By this I mean that I fixed the direction V, and I went L in that direction. So I could also fix other directions. I could go in this direction, and because we have an underlying lattice, the system is not isotropic. So it's possible that going in a different direction will be something else. So maybe that's L times V. So on the level of the law of large numbers, you can look at the passage time, T0 LV. That's the length of the minimal path, or the passage time. And you can ask on the level of the law of large number, how does that scale? So the law of large number would be something like T0 LV divided by L. Indeed, if the weight distribution is uniform in 1, 2, then every edge you use has a weight at least 1, and at most 2. So it is clear that the minimal length to go will be of order L. This is obvious. But does this converge somewhere? So it turns out that it does converge somewhere. And on the slides, I've written that as mu of V. This is predicted, and as I'll say in the next slide, this is actually proved. So on the first order of magnitude of the order of the law of large numbers, the passage time is some constant times L, and the constant could depend on direction, in fact, does depend on direction. Okay, perfect. What is the next order of magnitude? Next order is the fluctuations. So I can ask about fluctuations in several ways. One possibility is to ask about the expected passage time, as it turns out, this first order has a correction on the expectation level, which is a power of L conjecturally, maybe with additional logs in higher dimensions, we don't know, but in any case, a power of L to some first order, and usually the power is denoted chi. Similarly, this was the expectation. Similarly, you can ask what are the fluctuations, the random fluctuations of the passage time, and they too should have the same scaling, L to the chi, like the first order correction to the expectation. Okay, and this is on the level of the passage time, which will be very important to us actually, but maybe when you start looking at the problem, the first thing you ask is not the passage time, but rather the geometry of the path. Which a priori is different. And then what the physicists predict is that this deviation from the straight line will have also a power low order. It will be L to the xi. L to the xi, again, and maybe there are logarithmic corrections. We don't expect them in many cases, but we don't know in general. So let me write it in this way. So xi is the exponent of height fluctuations. Chi is the exponent of length fluctuations. Two exponents are in the picture. And so this is just to give notations, but what is expected of these exponents? The physicists tell us that there is a scaling relation, that chi equals 2 xi minus 1, so that in particular the height fluctuation exponent, this guy, is at least a half. So they tell us that xi should be at least a half. As we will see in a moment, this is actually related to the law of large numbers. So going back to something that we went fast with. What are the values of these exponents? We don't know. We don't know, except in 2 dimensions. If you are in 2 dimensions, then there is something called the KPZ universality class, which predicts for us that the length fluctuation exponent is 1/3 and the height fluctuation exponent is 2/3. This is a prediction, not justified in this model. And in any other dimensions, we don't know. And in particular, it is open in the physics literature whether this chi exponent, whether the exponent of length fluctuation is positive in all dimensions, or even more strongly, whether the standard deviation even goes to infinity. And by the scaling relation, the question is whether the height fluctuation exponent is strictly bigger than a half or not. So the physicists are telling us that this is always at least square root L, at least like a Brownian motion, but is it more than that? We don't know if there is some dimension where it's exactly square root L. We don't know, and that's an important question. The physicists don't know either, so it's a very interesting open question.
Sorry, is the scaling relation something that has been proven, or this is
not quite proven, as we will discuss? Not quite. Right, but it is predicted nonetheless. And then let me also return back to the law of large numbers, to the first order of the length. Then this mu of v, as we said, depends on direction. A nice way to visualize mu of v is to consider all the places in space where mu of v is less than or equal to 1. So in some sense, I'm giving you a budget of L. I ask you start at the origin and reach all points in space that you can reach with length less than L. That's your budget. Where can you reach? And that will define for you some sort of a ball, so to speak. You start at the origin and all the points you can reach with the budget of L, that's, it's kind of fluctuative, but roughly speaking, it's some kind of ball. And as one can actually prove, this is some kind of ball. That is, there is some deterministic shape upon which you have some smaller order fluctuations. And this deterministic shape, this is given by these values mu of v, and it is what we call the limit shape. And a basic question in the picture is, how does the limit shape look like? It's expected to be strictly convex. It's further expected that if you take the tangent at any position, then when you magnify it, then it has a second order Taylor expansion around that point with a positive second order. So So when you deviate epsilon to the side, the deviation here should be epsilon squared. That's what I'm saying. So this is expected like a ball, to behave like a ball, although it's not believed to be a Euclidean ball ever, but or it's unknown at least. Okay, and it depends in particular on the weight distribution. You take the weights to be uniform 1, 2, or uniform 1, 3, or so it matters. Okay, these are the predictions. What is actually proven among all of this? Very little.
Since a prediction, is it also like a computer simulation type thing where you can see this shape?
You could, and some people have. It depends on the dimension, of course. So mostly in 2 dimensions, it's a bit easier. It seems that it is not a ball, even in some cases that are a bit simple, like the exponential 1 distribution for the weights. Yeah, so you could see it a bit. Yeah, of course, you can only do finite size simulation. But the existence of the limit shape has been proven. So this is the good news. It has been shown that mu of v is well defined. The bad news is that we don't know almost anything about it. So again, I see all of my peer animations went bad here. But in particular, these are kind of degenerate cases of the possible limit shape, like the L1 ball and the L infinity ball. We don't know to rule them out. So the most basic thing we don't know how to say. So let me just explain to you how ridiculous this is by giving an example. If you start in 2 dimensions from 0, 0, and you aim to go to L0, well, to the first order of magnitude, this costs you some cost, C1L. Now, suppose you want to go to LL, which a priori, you'll need many more edges to get there, because the minimal number of edges to get here is L, minimal number of edges to get there is 2L. Well, if you want to go there, it's going to cost you C2L. We don't know that C2 is different from C1. We don't know that it actually costs you more to go diagonally than to go straight. It's possible that this path to the first order of magnitude has the same length as that path. We don't know to rule that out. So that's rather ridiculous, I would say. Of course, if the distribution is uniform on a small interval, say 1, 1.5, then just by the fact that this must have more edges, you know that the constants are different. But if the distribution is uniform 1, 10, then you don't have this simple argument, and we don't know. So that's rather ridiculous. So this is something to think about. Would be great if you can improve upon that. And similarly, we don't know to rule out the L1 unit. So this is on the level of the law of large numbers. What is known about the exponents of length fluctuations and the exponents of height fluctuations? Very little. So we know that the exponent of length fluctuation is less than 1/2. The standard deviation is less than square root L. And we actually got an improvement of that by a square root log, which was a big breakthrough. The square root L was known for a long time, since Kesten, and this is more recent by Binyamin Nikolai Schramm, using influence bounds, Talleyrand type ideas, gave you another square root log L. This is in any dimension. In dimension 2, we also have a lower bound. We know that the standard deviation does go to infinity, at least as square root log. And that's all we know. So in dimension 3, we don't know that the standard deviation goes to infinity. As I said, even in physics, they don't know exactly. And from above, we don't have anything better than square root L with a log correction. So we are really in poor shape about the exponents. On the level of exponents, I might say that chi is between 1/2 and 0. Pretty poor. And as I said, in 2 dimensions, chi is supposed to be 1/3, but we don't know. Okay, what about the transversal fluctuations, so the height fluctuations? So as I said, I may expect that the minimal path between these 2 points is close to a straight line. How close can we say that it is to a straight line? Well, we cannot say. So it is open whether the deviation is little o of L. So we cannot say that the optimal path is not a macroscopic triangle. We do not know that in the midpoint it doesn't go through, if this is L0, it doesn't go through L over 2, L over 2, say. It doesn't do like that. We don't know that. This is related to the previous question of showing that going at an angle costs you more. If we knew that, so if we knew to rule out the L infinity unit ball, we'll also get that. But we don't know. All right, so that's a bit disappointing. On the positive side, we do have a lower bound on the transversal fluctuations. We know that they are at least of the order L to the 1 over D plus 1. So better than nothing. At least we know it's not a straight line. It fluctuates a little. But the physicists told us that it should always fluctuate at least like square root L. So we don't know that in any dimension. But it's also related to the limit shape. It's related to the scaling relation. What about the scaling relation, which I remind you was chi equal to psi minus 1? Well, we have conditional proofs of it. If you assume that the exponents exist in a very strong sense, then you get it by Chatterjee 13 and Uffinger-Damron 14. But those are conditional proofs. Okay, so situation is very poor. But still, I wanted to emphasize these open questions and tell you about some results. Let me say that there is some detailed understanding for related integrable models, which only appear to exist in 2 dimensions. So there is a model called directed last passage percolation, and in that model, it appears that that model is integrable. So there are some directed last passage percolation models for which we can calculate everything. We can prove that the exponents are 1/3 and 2/3, and we can get even much stronger. So I wrote here CLT. So in fact, in 2 dimensions, the limit distributions after proper scaling are not Gaussian. They are Tracy-Widom, and we know much more about the process limit and so on and so forth. But all that in a related model. For first passage percolation.
Can you say something about what is integrable and why this model is not?
Right. So the word integrable is a bit vague. I use it in a very rough sense. I just mean that there are exact formulas for something. So by integrable here, I mean that the passage time between 0, 0 and L0 will admit some integral formula with some large determinant of large matrix, so some determinantal process in the background. So there's some exact identities. The starting point is the Robinson-Shenstedt-Knuth combinatorial correspondence between permutations and the Young tableaus, which can be generalized to this setup. Maybe indeed to emphasize further the connection with permutations, let me say the following, which is nice. Imagine that you do a continuous type of model of this type. So here the model is on a lattice. Let's do it in the semi-continuous as follows. The x-axis is still going to be a lattice. So this is going to be a lattice, but the y-axis is going to be continuous. And let's do the following. Let's put, this is 0, this is 1. Let's put in this interval of length 1, a single point uniformly distributed. So here is my point, x. And then here also a single point uniformly distributed, and so on, for each one independently, including, say, the last one, including even the first one. So, and now I'm going to do a directed first passage percolation. That is, I would like to find the path that goes from here to here and only goes up, right and up. Only goes right and up, and this is a last passage percolation instead of first passage, so I want to catch as many points as possible. So in my model, I'm going to try and catch as many points as possible by only going right and up. Maybe this is the one. So this is a similar thing because we have a random environment and we're trying to find the maximal path, not the minimal, the maximal, but it's very similar because it's directed, then it's the same really. But if you think about this, because the location of the points was a uniform random variable, then this is the same as a random permutation. All that matters is whether a point is higher in y-axis than the other. So we actually have a uniform permutation, and what we're looking at is the longest increasing subsequence of a uniform permutation.
That's why it's rhythm.
That's right. So in fact, the problem in this setup is equivalent to understanding the statistics of the longest increasing subsequence of a uniform permutation in Sn, which has all these formulas associated to it eventually through the Robinson-Shenstedt-Knus correspondence that takes a permutation, returns Young tableaus, and somewhere there is a determinantal process.
But people call a model integral after they found some formula.
Yeah.
So initially somebody.
That's right. So it is a meaningful statement to say that we don't know if this model is integrable. So maybe there exists a formula that we've missed. But all the models which are first passage percolation no formula of this sort has been discovered. So it's possible that they are not integrable, but we don't know for sure. It's kind of a co-RE, I guess, or RE. Okay, so this is what we have rigorously on the basic predictions. I want to tell you a few recent results which improve upon the state of the art. They do not improve upon anything written on this slide. They improve in a different direction. But still, I would like to tell you about them and explain an idea of proof. So we have a 2-hour seminar today. I'd like to explain altogether 2 ideas of proof. One of them will be what will be done now, and another on minimal surfaces later in the talk. Okay, so let me tell you about a related open question and the progress that we were able to make. So here is the open questions. So we will talk about the influence of edges. You know, if you come from Boolean function analysis, for instance, then you might say, let me give each edge a weight which is either 1 or 2, just discrete, 1 or 2. And let's ask about the influence of a single weight on the total length. That makes a lot of sense. But what is that influence? Well, in some sense, it is just this. You're asking whether an edge lies on the geodesic between 2 points. That's the basic object you'd like to understand. That sounds kind of reasonable, but you know, I fix my edge here. Here is my edge E. I want to know, does the geodesic pass through it or not? Well, it seems to be related to the transversal fluctuation, because if the geodesic is very fluctuative, it shouldn't pass through here. And if it is very concentrated, maybe it does pass through here. So here's a basic challenge, seems trivial almost, and which goes back maybe even to Kesten, but got the name Benjamini-Kalai-Schramm midpoint problem. Let's ask, does the geodesic pass at the mid edge? What does the mid edge mean? So I take the geodesic from 2 points, say 0, 0 and L 0, and I take the edge which lies near L over 2, 0. Does the geodesic pass here? Now we've already said that we know that the transversal fluctuations are a little big. So then you could imagine that with that, it is unlikely that it passes exactly on that edge because it is a little fluctuative. However, this result is only on average. So we know, say, that 90% of the vertices are a distance of this size. We don't know that the middle one. So you understand, we know that mostly the geodesic is high, but maybe when it comes close to the middle, somehow it remembers that it forgot something, goes to the middle, and then goes back to being high. We don't know how to rule that out. That's so strange. So that's another question to think about. So this is the Benjamini-Kalai-Schramm midpoint problem, just to show you how ridiculous the situation of the subject is. So actually, this problem has been resolved in the sense that we know now that this limit does equal 0. So we know it is unlikely to go to the middle edge. It's been shown by Alberg and Hoffman following an earlier proof that was under assumptions by Dameron and Hansen. However, the proofs are non-quantitative, so we don't know the rate. More generally, one may expect that the only edges which have, if I fix the probability to pass through the edge, say 1 over 10, then the only edges that will have 1/10 probability for the geodesic to be on them should be in a small ball around the endpoints. That should be the only edges that actually have a good chance, and all the rest should have small chance. That's more general. Now, in a joint work with Dor Elboim, who's here at the IS and sitting in this room, we were able to make, and I forgot to mention that Ken Alexander in all dimensions, not just two, got a quantitative version, but under assumptions that are still unverified, on the existence of exponents and limit shape and so on. So we were able to get a quantitative version, so to improve upon the state of the art by getting something quantitative. And here it is. So maybe I'll use the board on the other side. What we were able to show is the following. So this is about coalescence. Maybe I'll go down, but it has as a simple corollary also the Binyamin Nikolai-Schramm midpoint problem. So what we were able to show is the following. Suppose I have two geodesics. One goes from, say, as this is in 2 dimensions. One goes, say, from 0, 0 to L0. And the other has a starting point that is not far. So it's somewhere in a small box here. And has an ending point which is not far. So it's somewhere in a small box here. So the side length of this box is going to be L to a power. Well, what we can do in our theorem is L to the 1/8 minus epsilon. And then you pick any starting point here and any ending point there. So you have two geodesics. You have the geodesic that goes from the original points, and you have another geodesic that goes from the new points. So this goes from here to here. And what we were able to prove is the following, which sounds a bit reasonable, that these two geodesics coalesce. So they share most of their edges. That's the coalescence result. And indeed, you may give it the following picturesque idea. There is a random environment, and in this environment there are highways and byways, because many people want to go from here in the general direction there, and it turns out that in the random environment there is the best way to do that. Now, if you don't start exactly at the starting and ending points, you take a byway until you hit the highway, you go on the highway, and at the end you split. This sounds reasonable. How far should I expect the distance between the starting points to be and still get coalescence? Because if you start very, very far away, you probably don't coalesce. Well, you may expect that this should be L to the 2/3. So L to the 2/3 minus epsilon. Why 2/3? Because that's the scale on which geodesics fluctuate. So if they fluctuate on this scale, they kind of hit each other and coalesce. That's how you may expect. But we don't know that they fluctuate on the scale 2/3. We only have the lower bound, 1/d + 1, which in 2 dimensions is 1/3. We didn't even get that, but we got 1/8. So this is our result. First quantitative result on coalescence. First result actually of coalescence between two fixed points. And this is what is stated here. You immediately get from this a quantitative result in the on the midpoint problem by the following argument. I'll only sketch that. Suppose that when you go from 0, 0 to L0, then you do have a good chance to pass through this edge. Then, if you instead go from 0h to LH, then you, by translation invariant of the whole picture, then you will have a good chance to pass through this edge. However, the two geodesics coalesce if h is small. So do they pass here or do they pass there? You may argue that they could pass through both because they could do that. Let's ignore that because that's something else, and anyway we can rule out in this picture. So let's just imagine they choose one edge on this vertical line. Do they choose this or that? They can't choose both. Well, because they coalesce. Now I take another point over here and another point over here. They all coalesce. They all go through the same edge. So that shows you that a single edge is not so likely, because is it the edge of the bottom? Is it the edge of the top? The edge of the middle? It has to be exactly one of them. So it can't be that likely. So this also gives a quantitative resolution for the Binyamin Nikolai-Schramm midpoint problem in 2 dimensions. And there are other corollaries that we could do. I'm not going to tell you the proof of this result, But I'll mention a different result for which I will tell you some ideas of the proof. But this is progress that was fairly recent, just published this year, put on the archive 2 years ago, published in GAFA. Okay, and this is the result that I will tell you something about, the number of influential edges. This is a paper we put a bit later. Okay, and then let me explain it on the board instead of on the slides. Another thing you could ask, the Binyamini-Kalai-Schramm problem asks whether you pass through this specific mid-edge. We solved that in dimension 2, and previously Alberg and Hoffman on quantitatively and Ufinger-Dameron in dimension 2. What about dimension greater than 2? We're unable to solve that still. We cannot show that it doesn't pass through the middle, but we got some result in the right direction. It's a bit strange. We could get that, but not the actual theorem, not the actual midpoint problem. What we could do is the following. Let's fix the starting point, 0, and the endpoint L dot V. I can ask how many edges somewhere in space, I don't know, how many edges have influence or probability to pass greater than 1/10? So the number of edges with influence greater than 1/10. How many? And as I mentioned previously, you expect the only such edges to lie in a small ball around the starting and ending point. We can show that the number of such edges is at most some constant depending on 1/10. So if I put here epsilon and most a constant depending on epsilon, no matter where the points lie, very far away, very close together, in this direction, in that direction, for any fixed 2 points, at most that many edges. So we cannot show that the mid edge is not one of them, but we can show that there aren't too many. So it's progress in the right direction, and it's there is also a quantitative related quantitative bounds, which is like what you would expect given this lower bound on transversal fluctuation. What I would like to tell you now, and I'll use the board for that, I'd like to tell you some ideas from the proof of this result. So maybe if there are questions, I'll take them now, and otherwise I'll move to the board for a little bit. Any questions? Yeah.
On the side, what's little d?
There is a little d. Yeah, sorry about that. The little d is a capital D. I needed to change all of them, and I forgot that one. Sorry. Because I'll use little d for something else in a moment. I wanted the same notation.
How much would the picture change if I would just be not shooting for the minimal thing, but like approximately minimal?
Right. So what does approximate mean? Say up to a constant?
I'll say 1 plus epsilon approximation.
1 plus epsilon. That's a very big deviation. So what does it mean shooting for? So you want to know how straight it could be?
Yeah, how straight it is. Yeah.
Well,
then it will be almost the straight line, I guess.
No, it depends. If it's 1 plus epsilon approximation, then you don't know. No, I don't.
Because on a finite, on like a 10 by 10 box, you can get as close as you want to the time constant, and then just
Okay, yeah, right. So that's right. There is something of this sort. So you could take if you want a 1 plus epsilon approximation, you could take a box which is some function of epsilon by some function of epsilon, such that if you go from the two, so this is C of epsilon by C of epsilon, such that if you now want to go from here to here, then there is a geodesic that does that, and with the time constant, so the leading first order behavior up to epsilon, the same as when you want to go from 0, 0 to L0. No matter how big L is, the ratio of this to L converges to a limit, and this limit is achieved already by a small box. And then you can paste these together. But if you paste these together, though, you will lose the second order correction upon pasting, and that would also be linear. It's a bit more delicate. Yeah. No, I can't, one would have to think a little bit. So it's a bit quantitative. How big should this box be before you're close to the limit constant? And our predictions on the rate of convergence, it has again this exponent L to the chi that I mentioned. So you want to know the expected the expected time, and I said it's linear onto first order and L to the chi to second order. Then the loss that you get when considering a small box is this L to the chi, and then when you string them together, you get the sum of these L to the chi's, and you want that not to be that. So maybe you can do that with the log. So right. So I guess maybe you can get as close as you want, but not to a constant. Maybe, yeah, because then you'll string together little of L boxes. Yeah. Okay.
So,
But this is not proven.
in this context, I don't see exactly the connection between influences and the Fourier coefficients. I mean, if we are in the analytic Boolean function field, then there is a connection, at least for monotone functions. And if you ask a different question, you ask how many variables, these are variables, how many variables have Fourier coefficient, the individual Fourier coefficient on this, just a character including them, bigger than epsilon. Or in general, how many Fourier coefficients can be large?
So I'm only talking about the influence, not the general.
So I'm
Yeah.
trying to
Right.
figure online, maybe you can tell me what's the different setting. If we look at Fourier coefficient in general, we cannot have too many big ones because the sum of squares is one.
Right.
Right. So here it's not the case. I guess anyway we have sort of infinite number of variables, but we can finitize it.
Right.
What is the relationship in this setting between the influence and Fourier coefficient? Because there is some Boolean function hiding there. I mean,
Right. I mean, you could still, if your weights take values in two points, just A and B or 1 and 2, then you could still define the characters. It's not a Boolean function. It's a real valued function, but still has a Fourier decomposition. And then you still have this L2 equality, so you get somewhere. And I guess what you will need to know is exactly the length fluctuations. If you're doing an L2, you can subtract the mean, but what's the second order? So exactly this L to the chi that we don't know so well. Here, I'm talking about the first order characters, the characters of linear characters, the ones just involving one edge. If you want to go to two edges together, then we already don't know the solution. So if you take, say, E1 here and E2 here, and you can ask what's the probability that the geodesic goes through both of them. This seems related, and or the covariance of passing through one and through the other. And we don't know. We expect the covariance, for instance, to decay with the distance, little l, between these two edges, but we don't have a proof of that. So
yeah, but I forget two edges, one edge. What's the just the question you're asking? How many edges can be influential? Right.
Right. So we expect
no
only around the endpoints.
No, but there is no a priori bound that we can get from some analog of Parseval. For more general setting, this is a particular setting, but you have a, family of Boolean functions or not Boolean, real valued functions. Can we get some bound on the number of large ones from some total energy bound or some sort?
So the sum of influences is of order n because the length of the geodesic is n.
So the sum of influences is at most L.
Yes. So the sum of all influence in the total world
you don't
is
want
like the
it to
expected
depend on
length.
that. You don't, yeah, okay, so you don't want.
No, but that means, usually we'll discretize to, an L by L box, or if you have any upper bound on the fluctuations, then an L by this
No,
upper.
but you want the bound that is independent of L. You want the bound that depends just on.
No, you don't have,
how
certainly
large
you
it
don't have that a priori.
Okay.
Yeah.
And it's
But that is
possible-
exactly what we're proving.
I know, I realize this, so I want to first
Yeah.
understand what's different than the Boolean setting. And second, is this result you receive as specific to this very model, or there's a family of real valued functions that arise in this?
We use the translation invariance, so it's somewhat important to us that just like in the picture that was here, well, here, that I said, why doesn't it pass through this edge? Because if you take an alternative starting and ending point, it should pass through that edge and it can't pass through all. That uses the translation invariant. I use that this geodesic has the same distribution as that geodesic. That's important. If that's not the case, then maybe by inhomogeneity of the graph, it could push things to go to the middle. So that's actually important, I think. But beyond the translation invariant, it's not so clear. Actually, the results, the non-quantitative results of Halberg or Hoffman, they work in a more general setting where the weights assigned to edges are not IAD, but even just a general translation invariant process or translation invariant and ergodic. So even more generally. So I don't know if your question about more generalities about changing the graph, in which case probably it's a good idea to take a group or something with translation variance, or about changing the weight distribution, or
I mean, it seems like from what you said, if you use translation invariant, is that also if you define the geodesic in a way that it cannot deviate by more than, you're limited in some sense.
well,
Geodesics then
on a group review.
Translation invariant. Well, maybe we should see the proof, then I'll ask.
Maybe you can do it on in some other translation variant setups. We've not tried. Other questions? Yeah.
So I'm just curious, like what's the barrier for using these translation arguments to actually get like this midpoint property in higher dimensions? Like what?
And the thing that is missing for us, I mean, this doesn't give the midpoint problem at all, but what we did have that gave the midpoint problem was the previous slide, which is this coalescence. Here is the previous slide. So what we were using is that the two starting and ending points, the two pairs coalesce. The thing which is useful for us is that in 2 dimensions, geodesics are ordered. So if one geodesic starts above another, then unless it goes around the starting point, which we have to rule out, so there is something to do. I should have mentioned actually that this does have a limit shape assumption, but we know how to verify it in some cases. So and it's exactly because of this going around. So our proof doesn't apply unconditionally to uniform 1, 2, but it applies unconditionally to uniform 1, 1.1. There's something but in any case, so if you ignore the possibility of going around, which we rule out, then what is important to us is that the top geodesic stays above the bottom geodesic. It cannot cross it. Indeed, we are deducing the coalescence by saying that there is coalescence at 1 point here, 1 point there, and then everything in the middle is the same. And along the way, it's important that it couldn't cross. And if you're in 3 dimensions, they could go around each other, so there's no ordering. So this ordering property is an important feature of 2 dimensions that is important in our proofs too. And there has been results of Ken Alexander, as I mentioned here, in the maybe in the previous slide, which work in any dimensions and give the optimal bounds, but under unverified assumptions. So in particular, Ken has found a way to avoid using ordering. So maybe that's the way to go, but so far it's under assumptions which are not verified. Maybe one can do better. Okay, we use the ordering.
So in 3 dimensions it doesn't coalesce, or we don't know, or do we know something?
So at least if the length fluctuation exponent, the standard deviation of the passage time, actually goes to infinity with the length of the exponents, then you definitely expect coalescence. And otherwise you might still, but I'm not completely sure. Because if you have 2 faraway points and 2 other starting points which are very close, starting and ending point, then one possibility for this guy is to go here, for this guy to go here and then to proceed exactly the same. And another possibility is not to do that and say to be disjoint. But if it goes here and here, then just loses a constant in the length. So you can ask, is losing a constant a big deal? Well, this has to do with whether the standard deviation of the passage time is more than a constant or not. So if the standard deviation is large, then losing a constant is not a big deal. So maybe it makes sense to coalesce. And if it is a constant, maybe you don't want to do that. It's a bit unclear. I don't know the full answer. Okay, other questions?
You have some prediction into dimensions, how many times the path will cross a straight line between 2 points?
Yeah, I mean, it should be that the if the path is has height fluctuation L to the xi, then roughly speaking, at every point it's uniform between minus L to the xi to L to the xi, and then the first moment argument would tell you that the times it hit the x-axis is like L to the xi divided by L. In 2 dimensions, that's L to the ones. That's the probability, and then what they say. So in 2 dimensions, when the height fluctuation exponent is 2/3, you will expect L to the 1/3 crossing of the x-axis. Because at any one position, you have L to the minus 2/3, so L to the minus xi probability to be at the x-axis, roughly speaking, and that's proven in these models of integrable models of directed last passage. In higher dimensions, I would similarly expect L to the 1 minus xi crossing, but we don't know xi. Okay. Other questions? Okay, so we're gonna say something about the proof. Oh, sorry, went too far. Say something about the proof of this result. So maybe if you can raise the board now. The screen. Excuse me, person recording. Can you please raise the screen now? Thank you. Let me, right, that's fine. So I hid before the beginning of the talk a lemma on the board. So I'm gonna, what we want to prove now, unfortunately not in the board, in this time, we want to show that there are not too many influential edges. So it's unlike, so there can't be too many edges where it's likely that the geodesic passes through. And this is a kind of delocalization result. So delocalization means that the geodesic is not a straight line, delocalized. So, and let me just give a principle. The principle that we're using for that previously was used in other forms, maybe weaker than us. The principle is to use a perturbation of the weights and translation invariance. This is very rough. And now we will see how this comes into play, how these two ideas indeed give us the result. Perturbation of weights and translation invariance. The lemma on the top, which looks a bit complicated, is the lemma on perturbation of the weights. There are other simpler lemmas on perturbation of weights, but I wanted to give you this one because it's very nice. You might be able to use it in other contexts too. It's rather general and it's stronger than the others. So I want to show it to you. So what's happening here? So we're going to have this mu is the distribution of the weights of edges. For instance, it's uniform 1, 2. Uniform 1, 2 is an example of mu. That's great, great choice. So just have this one in. Okay, and then this lemma on perturbation of weights is saying roughly the following. So we're going to look in some finite domain. And in this finite domain, we have many edges. We're going to pick some subset of the edges. And we're going to say, well, the subset of the edges, they got some weight. Suppose I perturb that a little. Can you tell that they made the perturbation? Is there any event whose, that will distinguish the distributions before and after? So I want to say, no, the distributions are rather similar. I'm only going to do that in one direction. That's the direction I need. But it's a useful quantitative thing. So let's try and read this. It's long and a bit complicated, but let's try to read it. So the main thing is that my perturbation is going to be called G sigma plus of t. So G sigma plus of t, it takes the weight, which is a number between A and B, and it increases it a little. So it's always at least what it used to be. It's always at most sigma more, but it's also many times more by sigma. So think about C0 as a 10 and take delta, which is 1 over 10. So when you apply G sigma of t, G sigma plus of t, you're adding sigma, adding a constant sigma. So in fact, the way you may imagine it is not quite that, but the way you may imagine it is that when you're in the bulk, then G sigma plus t is going to add sigma. But you can't always add sigma, because when you're at the edge, it doesn't work. So when you're at the edge, you're going to add a little bit less, so maybe half sigma. And when you're really at the edge, even less than that. And then that's why we have this funny subset, B delta. On the subset B delta, you add the delta sigma. And the subsets B delta are almost everything. When delta is small, their measure is going to 1. So you usually just add sigma. That's how you should think about it. So there is a way to add a certain amount close to sigma to the weight of an edge. And then the distribution is not so changed. In what sense? We have this funny, we have this quantitative version. For any event A, any event that you want, completely arbitrary, the probability of that event after the perturbation of the weights is comparable to the probability of it before the perturbation of the weights. We only need the one-sided bound. You could try to devise a two-sided bound. We're not interested in that. We just need the one-sided bound. So after perturbing the weights, the probability of the event is not much smaller than what it used to be. At most, what it used to be to a certain power with some prefactor. What is important, what have we done to the weights? To the first one, we added S1. To the last one, we added Sn. Altogether, we added S1 up to Sn to the weights. What is important is that the L2 norm of what you added is not too big. Let me give an example. So the example is not in this realm, but it will be a good example to keep in mind. Imagine that your random variables x1 up to xn are IAD normal 0, 1. And now imagine the following simple idea. Just go ahead and add epsilon to each of them. Can you tell that the distribution of this vector is different from the distribution of that vector? So that's a bit of a funny question. What test could you use to distinguish the two distributions? Well, one test, which is actually the optimal test, you could ask for the average of these numbers and check if the average is, I don't know, at least epsilon over 2, say. Well, then you're going to want to choose epsilon in a way that this test doesn't distinguish the distribution. And for that purpose, we're going to choose epsilon of the order of the standard deviation of the average. So what I'm claiming is that if epsilon is of the order 1 over root n, then these two distributions are, for instance, their total variation distance is between, I don't know, a quarter and 3/4, say. It's not very singular to one another. And 1 over root n is what you can do, and this ties in with this L2 norm here, because I'm going to add S1 to the first variable and up to Sn to the last variable. L2 norm is what's important. So long as that's not too big, the two distributions are similar. But even if it is big, you have a comparison. Okay, this is the perturbation of the weights lemma. I wonder, maybe we are supposed to break in the middle, right?
It's up to you, but yeah, that's natural.
That's natural. And how long is the break?
5, 10 minutes, you choose. The speaker is.
I don't know how tired you guys are.
You can decide according to how tired you are.
Right. Okay, let's do 5 minutes. We had a lot of questions.
Okay.
Let's do 5-minute break. I also use the time to write a little on the board. And then I'm going to explain how this lemma can give us the result about the influences. I won't have time to go into all details, but it's not complicated. And the lemma, the proof of the lemma is also not complicated. You can do the Gaussian case, which is really easy, and then just consider the bijection that maps the distribution of the Gaussian to the distribution mu. Just that will work, actually. The Gaussian case is direct, and then map Gaussian to mu, and you get the lemma. It's not that hard. Okay, so let's do a 5-minute break then.
Right.
Thank you. That's the geodesic from U to V. So I sometimes write it as gamma, and I sometimes write it as gamma UV. And then if you ask for the influence of an edge, the probability that E is on the geodesic, then the theorem says that for every epsilon, the number of edges with more than epsilon influence is at most C epsilon. That's the result, and we would like to prove it. So let me give some ideas of proof. And the dilemma over there is going to be used. As I said, the proof of dilemma is not hard, but I won't have time to say it. So ideas of proof. So we're going to show the following. There is a goal. The goal, and the picture is relevant to the goal, that there exists some small c0 such that for every x in zd with the norm of x smaller than, I should have, sorry, there was something I should have done earlier. Let's define E to be the set of edges that I'm interested in. So E is the set of edges whose influence is indeed greater or equal to epsilon. So this is the set of edges that I'd like to show is not too big. Let's just define that. I'm fixing U and V. I'm not saying that, but I fixed it. I may as well assume that E is not empty. Otherwise, there's nothing to prove. Okay, and then when the norm of X is less than square root of the size of E, then the expectation of gamma X and the expected intersection of gamma X and E is at least some C size of E. So I could have added here the exists C, but little c is going to change from line to line, whereas C0 is not going to change. So that's the convention. But anyway, to clarify the point now. So what is gamma X? Gamma X is gamma of U plus X and V plus X. So let's see what we're doing. We're taking starting and ending points which are very close to that of U and V. We're going to use the translation invariance. So we're just going to copy the starting and ending points by translate them by X. By translating translation invariance, the new geodesic gamma X has the same distribution as the old. And we're going to ask, does the new geodesic intersect not exactly the old, but rather the edges which were influential for the old geodesic? Of course, it should intersect the edges which are influential for it. But no, I wanted to intersect the edges that were influential for the other one, for gamma. And what we're going to show is that its expected intersection with those edges is at least some fraction of them. So that's important. These constants all depend on epsilon. So I should yeah, okay. C0 does not, but C is going to be, or no, actually, no, both of them depend on epsilon. Sorry. Yeah. So I'm going to fix epsilon to begin with, and I'm going to fix UV as well. Okay, the constants depend on epsilon. Very good. And why does this suffice? Now notice this suffices. This suffices. And here is where the translation invariance is going to come in. Let me consider the sum over all x in this ball. So let me define the B to be all these x's. B is the set of x's such that the norm of x is less than C0 square root of the size of E. So the sum over all x's in this ball of the expected intersection with E. This is our basic quantity, and now we're going to work with linearity of expectation and get some contradiction unless the the theorem is correct. So on the one hand, by the goal, this is at least the size of B times C0, the size of E. C, I guess C, the size of E. Okay. And that's at least C0 times C times the size of E to the power 3/2. Okay, so that we have. Now, on the other hand, what is written here? This is really the sum over all x in B, the sum over all the edges in E, of the probability that gamma x, that E belongs to gamma x. and we're going to exchange this sum, and we're going to use the fact, we're going to use the translation invariant. Maybe I first use the translation invariance. So this is equal to, by translation invariance, to the sum over all x in B, the sum over all E in E of the probability that E minus X belongs to gamma. So instead of asking whether E belongs to gamma X, I'm going to ask whether a translated version of E belongs to the translated geodesic gamma X, and that's by translation invariance. And now I'm going to exchange the sum. So actually what's written here is the sum over E and E of the expected intersection of gamma with E. The expected intersection of gamma with E plus B. Right. So I'm asking, I have an edge E, and I have a small ball around it, E plus B. And I'm asking, what is the intersection of my geodesic with the edges in the ball? My geodesic is going from U to V. How many edges in this ball could it use? What's the maximal number of edges in a ball that my geodesic could use? Can it use all of them? Can it be like a piano curve, winding through all the edges of this box and still be a geodesic, still be minimal? Can it do that?
I guess it's like the side length of the ball or something.
That's right. It's at most the side lengths, because once it knows where it wants to enter and it knows where it wants to exit, then it could, if it wants, just take a straight line. That, if the weights are between 1 and 2, that has length which is at most the number of edges there. But if it did a piano curve, it can't have saved much, because each edge costs you at least 1 and at most 2. So by the boundedness of the weights, the number of edges in this ball is at most the side length of the ball, so less than the radius, to write it like that, of the ball, and maybe times a constant, some capital C. And the radius of B, by definition, is this square root of E. So altogether, we get the capital C, the size of E, and this radius of the ball, which is square root of the size of E. So the conclusion is that the size of E is at most some C, some other C, when the dimension is at least 2. Right, here the dimension entered, sorry about that. I wrote it as if it's in 2 dimensions, but the, sorry. Here we had the size of B. The size of B is, it's the volume of B, so it's the radius to the power dimension. So altogether it's 1 plus D over 2, sorry about that. Got confused there. So this is 1 plus D over 2, and if the dimension is at least 2, then this power is greater than the power of E here. So the only way to resolve the contradiction is if it is not too big. So this is enough for us. So we just need to show the goal. And now, I don't have as much time as I want, so I just give idea of proof of the goal. How to show the goal. So we're going to use the perturbation of weights, and we're going to use another idea which was already mentioned. Let me explain that. So let Tx be the length of gamma x, and T be the length of gamma. So another fact we're going to use is that the geodesic gamma x cannot have much longer length than the geodesic gamma. By how much could it differ? How much bigger could it be?
2 times x.
Yeah, at most some constant x, because the weights are bounded, so it could just go to that, do the same, and go back. So deterministically, the difference between Tx and T is at most some constant x, the normal x. That's deterministic fact. But we're going to get a contradiction in some sense to this fact after perturbing the weights. So let's see that. So we're going to use the lemma, use the perturbation lemma. By the way, in some contexts, this is called a Mermin-Wagner type argument, this perturbation, although I started to dislike that name. Let me not go into the context. So that means you call it the perturbation lemma. So use the perturbation lemma with S, which is 1 over square root of E times the indicator that E is in E, with SE. So what am I saying here? I have my, my geodesic gamma, and I have the collection of edges E. The collection of edges E, maybe there is an edge here, there is an edge on the geodesic, another edge on the geodesic, another one here. I don't know, this is the collection of edges E. I'm gonna increase the weights of the weights on E. On the set E is a deterministic set, it's the set of influential edges. I'm gonna increase their weight. I don't know how big the set E is, but each weight I'm gonna increase by 1 over the square root of the size. And the good thing about this choice is that its L2 norm is order 1. So it doesn't change the probability of events too much. So I don't know how big the set is, but I'm gonna increase the weight of each one by 1 over root E. That's the maximum I can increase it by and still have a bounded L2 norm. And now let's do this a little bit heuristically because I don't have the time to. Well, okay, I can do a bit more before I go heuristically. So let delta 0 be small. Let delta 0 positive and small. What can I say of the passage time t plus? So what is t plus? I've increased the weights of these edges. The geodesic gamma changed. What is the new geodesic? The new geodesic is called gamma plus. So when I increase the weights, gamma becomes gamma plus. T, the passage time, becomes t plus, and also the other geodesic, gamma x, changed and became gamma x plus, and its passage time became tx plus. I hope the notation is clear. What can I say about the new passage time, t plus? Well, it has to be bigger than the old passage time because I've only increased the weights. Has to be bigger, but I'm saying it is bigger by a definite amount. How much? Well, I claim it's bigger than what it was by delta 0 divided by square root of the size of E times the intersection of gamma plus with E and the set of edges with weight. The weight is called tau E in this set B delta 0. This is relatively clear. Let me explain the notation. B delta 0, that's the set of that's the subset of E which actually increased, because not all edges increase, because again, if you're at the edge, you don't increase. So most edges increase. So that's the subset B delta 0. For those edges which increased of the set E, and my new geodesic actually passed through them, I increased by delta 0 divided by square root E, and you can easily convince yourself that this relationship holds. On the other hand, what can I say about t plus x? So this is the passage time of the new geodesic in the other geodesic in the new environment. It also increased, they have to increase, but they say it didn't increase by much. It's at most what it used to be, plus the maximal possible increase of a weight is C0 sigma. So at most some C0 divided by square root E, and then gamma x intersection E. Here it's gamma plus, here it's gamma without a plus. When you think about it, it becomes clear, but it's not so important now. So this weight increased by a certain amount, and this weight did not increase too much. unless gamma x intersects E, in which case it could increase much. But that's what we want to show. That's our goal. Our goal is to show that gamma x intersects E. So if the goal is not satisfied, then T plus did not increase much. But T did increase much, and they're not far away from each other. So that's where the contradiction will come from. So all we have to verify is that this set is not too small. Not too small with probability greater than some constant depending on epsilon. That's what we need to show. Well, this is not important. It's very hard for the weight of an edge to be that in B delta 0. It has a very small measure. Let's ignore this one. So the only question is why gamma plus intersects the set E a lot. Well, we can ask a simpler question. Does gamma intersect the set E a lot? Well, by definition, this is the set of influential edges for gamma. So the expected intersection is at least epsilon times size of E. Actually, by Markov's inequality, you can deduce from that the probability that the intersection is less, that the intersection is at least epsilon over 2E is at least epsilon over 4. I lost the number here, is at least epsilon over 2. So just from the expectation and Markov's inequality, reverse Markov's inequality, if you will, you can get that there is a chance that gamma intersects the set of its influential edges on a proportion of positions. But we don't want gamma, we want gamma plus. Does gamma plus intersect the set of influential edges? That's unclear. But that's where the lemma enters. If gamma has a good chance, then gamma plus has a good chance. If in the old environment the event had a good probability, then in the new environment it has a good probability. It doesn't matter what the event is. So we're done. Okay? That's the idea of proof. So you use the perturbation of the weights and the translation invariance. This was the principle that we said we were going to use. Okay? And this is how this theorem in our paper is proved. We have a few other theorems in our paper, but this is a full, more or less full proof of that. Questions about it?
Can you remind us how you get the perturbation of weights? You just kind of think of like a resampling.
So when it was here, I guess it was clear. When you have a vector of Gaussians, I'm just going to add, just add. So it's a coupling. Okay, I take the old weights and I perform a deterministic operation to them. For Gaussian, the deterministic operation is adding whatever I want to add. Very simple deterministic operation. Here, it's a more complicated operation, which is encoded by this bijection, but the bijection is basically adding except on the side. I mean, actually what we do, we map the Gaussian to the distribution, so it doesn't exactly add in the center either, but it's more or less.
Sorry, I guess like, why are we allowed, can you remind us why we're allowed to add the...
So it's a question whether it was clear already for the Gaussian, which I did not explain. It's a calculation, or you can see it by rotation invariance of the Gaussian. You wouldn't be surprised if I told you that for a single Gaussian, you cannot distinguish between x1 and x1 plus, say, 1. You can distinguish, but not with very high probability. That wouldn't surprise you. Now apply the rotation of this vector so that the added vector becomes in one coordinate, and it will become this situation. That's another way to think about it. Or there's a nice calculation you can do with Helder's inequality that gives this. I prefer that. But in any case, for Gaussian, there are several ways to see this. And the same would be true if I take epsilon 1 up to epsilon n, so long as the norm of epsilon is bounded, say, or some other and then the L2 norm. And then there is a way to map the distribution, the normal 0, 1 to the uniform distribution, or whatever you have, just this usual thing we learn in the introduction to probability, that any distribution can be written as an increasing function of the uniform distribution. So you can map, and the addition here becomes an addition there, but slightly perturbed by this map. not much, it's a Lipschitz map under these conditions. Okay. Sure, I didn't go into the proof, but it's under these conditions and using the map that I mentioned, it really works. And we have a more general analysis. Okay, can I ask for the screen to be pulled down? Thank you. Is there any other questions while we wait? Are there any? So I told you about minimal paths in a random environment. In the remaining time, I'd like to tell you about minimal surfaces in a random environment. Again, questions and results, and similarities and differences and so on and so forth. So as you can imagine, minimal surfaces is not any easier a priori, although in some cases it could be a little. So, I mean, okay, you will see. So now we're going to talk about minimal surfaces, and the way we're going to do it is using minimal cuts, you will see. But we have in mind the following idea. I'm going to fix boundary conditions, and the space, you know, has random weights. So I started with RD and I made a perturbation of the weights. And now I'm going to try and find the surface that in some sense has minimal weight and interpolates the boundary conditions. This is a generalization of what we just did. Before we took 2 points and we wanted the minimal surface that interpolates the 2 points. The minimal surface was a path. Now it's a surface. We're going to first talk about surfaces of codimension 1. That's easier to discuss. I mean, that's mostly what we're going to discuss. Now, I want to create such surfaces in a nice way. Here is a nice way that we have found. We might be the first to study it in math, but it was, I mean, related concepts were studied in physics. Do I have another? Yeah. So here is a way to define a minimal surface. It looks a little different from what we did before. It's not so different from the geodesic case. Let's see it. So we're going to assign edge weights just as before. So each edge of the ZD lattice gets a random capacity or length, if you will. Let's call it capacity now. Let's say they are uniform on 1, 2 again. And now how to create a surface? We're going to do the following. Take a big cube in the ZD lattice. Here is the cube. There is the upper half of the boundary of the cube and the lower half of the boundary of the cube. We're going to ask for the sets of edges which cut, which separate the upper half from the lower half. And we're going to look for the minimal cut, the subset of edges that cuts any path from the upper half of the boundary to the lower half and has minimal sum of capacities. So we get a set of edges. The set of edges is dual to a plaquette. So now I mean, what I said so far is in any graph, I guess, you can do something. But now I'm going to say that it's dual to a plaquette. This is more a ZD thing. So when you have an edge in any dimension, you can talk about the little face like that, facet, I don't know, that is orthogonal to the edge and passes through its midpoint. The 1 by 1 by 1, d-1 dimensional facet or face, d-1 dimensional. And if you take the set of edges of the minimal cut and take the dual little plaquettes, they together form a surface. And that is a minimal surface that interpolates the boundary condition. What is the boundary? Because I separated the upper half from the lower half, on the boundary I'm at height 0, so to speak, at the height of the separation. And in the middle, it could do something else. If you do it in 2 dimensions, so you do exactly what I said in 2D, you want to separate this part of the boundary from that part of the boundary, then you separate via a path. I mean, again, if you look at the dual of the edges you pick, it's a path. And this exactly becomes the previous first passage percolation that we studied in 2 dimensions. Exactly, except that the path cannot escape the box now. But that's a boundary issue. But now I'm going to do that in 3D. And then I'm going to get one of these surfaces. So I don't know how to draw a surface with that. Okay, but you have a picture here. So this is what we want to study. Now, I go back a little to the notation. D is the dimension of the surface. N is the codimension. That means that altogether the ambient dimension, capital D, is D plus N. So everything lives in a capital D dimensional space, and we're researching a D-dimensional surface, and our codimension is 1 in this case. So in what we just said, N is 1. Okay? So I hope the model is clear. And again, the same questions, we would like to know how flat is the cut. I don't know if you have a guess. Will it be flatter than the path? We can do it in 2 dimensions. We have a path, and it has a certain deviation, conjecturally L to the 2/3 if you do it on an L by L box. So here it's also on an L by L box. Now you do it for surfaces in 3 dimensions. Is it flatter or more rough?
Offer money.
If I had money.
Flatter?
Okay, we have one for flatter, and the others? Going once?
Rougher.
Rougher, okay, very good. So let me say it's actually flatter, because to pull yourself up when you're a surface, in some sense you have to pull more, because you're kind of pulling it and more edges are added. It's a bit harder to do it. I mean, you have to add more edges for any fluctuation.
Is it true that if you cut it with a hyperplane, you get geodesics, you get something similar to the one?
What I just said is not a rigorous argument. I don't have a proof that the higher dimensional case, the fluctuations of it are less than or equal than the lower dimensional case. I don't have a proof of that. And it's also not true that if I cut it in a hyperplane, I get the previous geodesics. That's not true, or at least no reason to think that. So
the fluctuations in a slice would be smaller?
Probably smaller, because the whole thing is actually fluctuating less according to heuristic, let's say. It should fluctuate less and less as you go up in dimension. Okay, so less than L to the 2/3. Who thinks that when we do it in 3D, it still fluctuates as a power of L?
It's still good.
All right, other possibilities, maybe power of logarithm. Maybe it's completely flat, maybe it's order 1. So we have a 2D surface, we have a 3D surface, if you do it in 4 dimensions, we have a 4D surface, a 5D surface, they should all become flatter and flatter. Will it ever be flat of order 1? So that's the kind of questions we want to understand. We want to understand how close it is, and also the capacity of the surface, which are related issues. These are like the length and the length fluctuation and the height fluctuations. Okay, so there aren't, I don't know any other works before us on this question, except for the first passage percolation case, which we already discussed, so I'll just skip. There is an additional motivation for the question itself. I don't know if this will talk so much to a discrete math audience, but I just wanted to mention this. You can think of it as a minimization problem of a Boolean function, roughly speaking. So it's an Ising model.
You
So
don't think that minimization problem of a Boolean function will capture the discrete math audience?
right, when I say this way, I do think, but then I want to say it's an Ising
What
model.
else? Yeah, it's yeah.
Right.
Ising model.
Okay, sorry, I take it back. I think this will capture the attention of the discrete math audience. What I want to say is a reformulation. It's exactly equivalent to the previous, but I don't know if you prefer that reformulation. Another way to say it is that every vertex of the box gets a sign, either plus or minus, and the set of edges is the set of edges which are between the pluses and the minuses. So I have a sigma from ZD to plus minus 1, and you have the boundary conditions. these boundary conditions are called the Dobrushin boundary conditions. And then you want to find your energy function is this sum where this is the capacity of an edge, and you want to minimize the energy subject to the boundary condition. It's exactly equivalent. But when you say it this way, then statistical physicists are interested. So this is the random bond Ising or disordered ferromagnet Ising model, and we want to understand the domain wall. This separation of plus and minus is called domain wall when you study Ising models. Because of the equivalence, statistical physicists are also interested in it. Okay, so how rough is it? So I'm going to give you a heuristic for the answer. I don't know the answer on a rigorous level, but I do have heuristics for the answer, and I do have a result. The result is joint with my former student, Michal Bassan, and my colleague, Shoni Gilboa. Let me first present the result. But then I will explain some conjectures and related things, and then I will explain why we think that way. So here is a result with Michal Bassan and Shoni Gilboa. Let's just consider disordered distributions, coupling constants on the edges, which are uniform AB. The weights on the edges are uniform AB. But now I don't say uniform 1, 2, okay? Not 1, 2. I want to leave myself a little slack of AB. And what we are able to say is that if the ratio B minus A over A is small, that means that the weight distribution is between 1 and 1 plus epsilon. Okay, so very concentrated weights. Then the surface is localized already in ambient dimension 4. So when you look at the 3-dimensional surface in 4-dimensional space, it's flat. What does flat mean? That means that when you ask about the height in the center of the box, then it's very likely that you will find it within a constant distance. So for any epsilon, there is a large enough constant such with probability 1 minus epsilon, you find the surface up to that distance. That's what localized means. So it's localized already for a 3-dimensional surface when this ratio is sufficiently small. Why the ratio? Why is it important to talk about this ratio? The ratio, you can get some intuitive grasp for it. Suppose the surface tries to fluctuate. Let me draw I'll try to draw a 3-dimensional picture. Let's see if I manage. One possibility for the surface is to be completely flat. Another possibility for the surface is to start to fluctuate. Let's just do the simplest possible fluctuation. Let's say it adds a step. I don't know how to draw that. I just make it worse. So on this, the height is 1, and on this, the height is 0. And here, the height was 0. Is it clear? The surface is flat, but there is a little step. What is the cost of the step? My weight distribution is uniform AB. So the sides of the step, the edges on the side of the step, they definitely cost me A. Nothing to do about it. So lose A times the boundary size. What do I gain? I gain, well, potentially when you're flat at a higher height, then the sum of the weights is lower than when you were flat on the lower height. What is the deviation between them? Well, here you added a lot of IAD random variables. Here you added a lot of the same IAD random variables. The difference between these two sums is like the standard deviation. So it's like the potential gain, you don't always gain it, but you might gain it, is like the square root of the volume of this step. So if this is L, and maybe I know this is L over 2, then what we're talking about is that here it's A L to the D minus 1, and here it's L to the D minus 2. But there is a coefficient, it's B minus A. So, I mean, it's basically the range in which you fluctuate times that. Maybe there is a square root. Yeah, probably there is a square root. So, that's how much you gain, right? I hope there is a, anyway. So, sorry, so this is like square root B minus A and I should have written L to the D over 2. That's what I mean. So, okay, if you use this heuristic, you see that it's not going to be beneficial for you to create the step, because what you want to know is whether A L to the D minus 1 is greater than square root B minus A L to the D over 2. And this D is the dimension of the base. So again, I remind you, capital D is little d plus 1. So the two exponents match when little d is 2. When little d is at least 3, then step is not favorable. So that's an argument one could use. At least it corresponds to our result, because we are saying it's localized when the base dimension is 3 or the ambient dimension is 4. So it corresponds to that. You do see A and B minus A entering. You may ask yourself, but according to this argument, yeah, probably there's no square root after all. Sorry about going back and forth with the square root. Anyway, you may say, according to this argument, it doesn't matter what the values of B minus A and A are. So that's a bit of a mystery. Why are we proving it only when the ratio of B minus A over A is small? So it's a question. It's a bit unclear. Here I just took the easiest fluctuation, a little step. Maybe that's not what actually is happening. But at least you get some idea of where A and B minus A might enter, and where the dimensionality might enter. And we're able to prove for that. And let me give you some conjectures for what happens outside of this regime. So we conjecture that in fact, the minimal surface delocalizes when this ratio is large and the ambient dimension is 4, the base dimension is 3. So we conjecture that our condition is necessary for base dimension 3. We conjecture that there is a roughening transition in the concentration of the disorder distribution, or the weight distribution. That to me is the most interesting, one of the most interesting conjectures here. I have a version of it which is easier to state, maybe easier to prove, but I don't know if I'll have time to present it here. But anyway, we've not been able to. In lower dimensions, even this argument is hinting that the surface delocalizes because the exponents are equal, and we indeed believe that it does delocalize. That should be easier. We think that is within reach, but we haven't done it. And for higher dimensions, it should always localize, we believe. So this condition is no longer necessary, but we're not able to remove it. Our proof requires the condition. But it's interesting that in this critical dimension, it might be necessary. There might be a phase transition in the behavior. And I will explain where these conjectures come from a bit later in the talk. There are some additional comments, but I think they're not so interesting to us. You can take other distributions instead of uniform AB, and which is a bit nicer, you can do a different distribution for edges which are orthogonal to the base and the other edges. And that actually allows you for a solid on solid one. So it allows some extra interest. Okay, I'm not going to explain the idea of proof of this theorem, which is actually not, I mean, some ideas are not that bad and some are hard. So I'm not going to go into that. I will say that the slides for this are on my website, and the slides do contain a sketch of proof. I will go over it very quickly now, but you can also find it on my website. Any questions on this result before we go on? And the next thing will be a reason for these conjectures and another proof if we have some time. I will introduce a different model. The different model is easier to study and will give better results, and in particular motivate some of what we've seen.
In the localized case, does this fall into some universality class, like you expected fluctuations to be Gaussian?
Well, when it's localized and our theorem applies, in that particular case, then it's white noise. So it will have exponential fall off of correlations, and so basically it will be zero the height will be exactly zero at 99% of the vertices, and the probability that the given vertex is in a excitation in some non-zero connected component of radius r will decay exponentially in the radius, or even in the boundary length of the excitation. So then it's white noise, and doesn't and the weight will be Gaussian, yes, because it's kind of a sum of these localized excitations. But this is when our condition is satisfied, not necessarily in all the cases when it's localized. So although maybe it's still reasonable to think that something like that would happen here, but that's definitely not proved in our result. Other questions? The same question will come up in the model that I will introduce now, and then the answer might be different. Okay, so no more questions. Then I go to the final model of this talk. We saw geodesics, we saw surfaces. Final model is going to put all of them together, but in a different way. Okay, and then we also answer some questions: existence of a non-constant ground configuration, question of Denvin-Garbin. I won't go into that. As I mentioned, there are slides of proof. I'm not going to go into them, but they are on my website for those who are interested. So sorry, it takes a little while to go through that. Maybe so my computer is a bit slow. We go like this, if that's fast. All right. So here's another slide of proof, another slide, questions, and this is the last one. So this is last model, which is joint work with Barbara Dembin, Dor Elboim, and my student in Israel, Daniel Hadas. So now I go back to this notation. D is the dimension of the surface, N is the codimension. And now I'm going to allow very general numbers. So previously, either D was 1 and N could be something, or N was 1. Now I'm going to allow, say, a 2-dimensional surface in a 4-dimensional space. Okay. So we've already spoken about first passage percolation, Ising model, so I go directly to our model. So we introduce a new model. It existed in some literature, definitely in the physics literature existed for more than 30 or 40 years, but in the math literature, almost nothing, and except in dimension 1 where there was a bit more. We introduce and study. Let me explain what this model is. It takes a little while to get used to it, but I hope you like it. It's not that bad. And the reason that we introduce a more complicated model is that it's easier to study, or it appears at least to be easier to study. And indeed, we can get much better results for it. So the idea is that we will study the model which is easier to study and at least have predictions on the behavior of the model that we first started with. At least have some access to it. So how is this going to work? So we're going to define surfaces as follows. Our goal is to define a d-dimensional surface in a d plus n dimensional space. As we discussed, the surfaces will be modeled by a function phi from zd to rn. Let me explain this on the side with some examples. So this is the case d equal 1, n equal 1. In that case, I'm going to put a copy of r above the axis, above z. And then my minimal path, or geodesic, or surface, it's going to be a general function like that. So it's just going to choose for every one of these real lines a number. In what sense is it different from what we studied so far, especially in the fact that it cannot go back upon itself? So previously, when we started geodesics, we said that the geodesic between 2 points can be rather wild In particular, if I take a specific vertical line, it could intersect it several times. Here it cannot. On every vertical line, it has to choose a single height. Okay? That's the surface. This is d equal 1, n equal 1. What happens for d equal 1, n equal 2? That means that at every vertex, I now have a plane. I have a plane, a two-dimensional plane, and my surface needs to choose a point in the two-dimensional plane. So maybe it chooses this point, and then that point, and then this point, and then I don't know. So because it chooses a point in a plane at every vertex, it is like a path in a three-dimensional space. Okay? So that's how we are doing it. That's why I say the codimension is 2. What happens if you have d equal 2 and n equal 1? That means that you have a lattice of points. And at every point you have a copy of the real line. And your surface needs to choose a single height at every vertex. So it is like a two-dimensional surface, in a three-dimensional space. It's a bit hard to draw. Okay, so I hope that it is clear why this models a d-dimensional surface in d plus n dimensional space, in capital D, which is d plus n dimensional space. Okay, now I need to introduce the environment, because all this should be done in a random environment. What is the environment? The environment is a general function eta from zd times Rn. Usually I will say to R, it's convenient sometimes to allow infinity, so maybe R union infinity. Where is this function in the picture? The function in the picture sits on these copies of R or R squared. So for instance, the function is here. Here I have the function eta. So this blue function is the function eta. It tells me every point that you pick on this line, how good is it? If the function is low, the point is very good. If the function is high, the point is not so good. So the geodesic or surface is going to try to find points of eta which are small in magnitude. And the function also sits on this plane. So the geodesic will try to find points in the plane which are small. And here it also sits on the fibers like that. Okay, so I hope it is clear where the environment enters.
What is the length for the geodesic?
The length in terms of the number of vertices of the base is fixed.
No, but yeah, what is the
length is this, but it will be introduced in a minute. So give me one more minute and you will see.
Because if you just choose the smallest value point in every, then...
So I have to penalize the jumps, and I will penalize the jumps. Very good. There is also an environment strength. It is not so relevant for our talk, so I just put it here. But if you want, you can take it to be 1 and forget about it. And then what is Avi's question is the energy, or the so-called Hamiltonian. In order, this is what Avi was asking. He was asking what is the length of a geodesic or surface. Now I will explain what is the length, or I want to call it energy. I prefer this name, but it is the same. So there is this, the function that gives the length is called h. H depends on the environment, and then assigns to every surface its energy. What is the energy? The energy is a sum of 2 terms. First, I consider all adjacent points in the lattice, and I ask what was the height change of the surface between the adjacent points, and I penalize the length by the norm square of that height change. That means that when my surface decided to make this big jump over here, it's going to pay the square of this jump. So it's not a good idea for it to make very big jumps because it's going to pay a lot. This is the so-called elastic energy, if you will. I mean, it might be called this way in physics, I guess, elastic energy. So my surface would like to minimize elastic energy, but it would like to balance it with a potential energy. Of course, if I just had this and nothing else, and my surface was zero on the boundary, it would just be zero. In fact, whatever it is, it would just be the harmonic extension of the boundary if I just had this. But there is another term that roughens the surface, and that's the term that takes into account the environment. So that's the potential energy. I add lambda, sum over all the vertices, and I take the environment, eta, at the location that my surface is at. So if my surface passes here, it gets the value of the blue function here. Passes there, gets the value of the blue function there. So my surface is trying to balance between the elastic energy and the potential energy that comes out of the environment. This is the environment potential energy. Okay? And once I have these definitions, I would like to minimize. So we would like to minimize h eta of phi over the functions phi, which equals 0 outside some domain. Outside the domain, minus LL to the D. So I fix that on the boundary, my surface is 0, and I want to find the minimal surface that corresponds to that. I can choose other boundary conditions. Actually, all that will do, as it turns out, but it's not obvious a priori, is to add the harmonic extension of the boundary values. So actually, it doesn't matter, but I could. And I could choose other domains instead of the cube. The cube is very natural, and I like it. Questions about the model?
So you should run to
finish. Yeah, right.
So the environment function, are there any condition on it? Or?
Okay, so the model may be defined for any given environment function, but I will choose it to be random, and I will choose specific distributions for it. I expect that there is a different behavior for different categories of environment, but perhaps within a category, it might be that there is some universality. So this will be the subject of the next slide. Or maybe the next slide is about the background. So as I said, the physics literature has a lot. The math literature only works in the D equal N equal 1 case, and in some case, and they work on a fixed D and N going to infinity, but focusing on a different aspect, so the number of critical points instead of the minimizer. So altogether, at least for surfaces, we are the first one. Okay, so coming back to the question that you asked about the disorder, so we're going to look at the so-called independent category. We have work in preparation on other categories, but let's try that one. So that means I try to make my environment as independent as possible, because I have in mind these previous questions where the environment was IID on the edges. So I want to make it IID. But of course, I cannot make it IID because the environment is sitting on fibers which are continuous. I can make it IID between fibers, but I can't make it IID on a fiber because it's continuous. So I do something that approximates IID. So what we do, we take a white noise on a fiber and we smooth it by convolving it with a bump function. So for instance, when the fibers are just on, so when the fibers are simply R, then I had the white noise, which is a distribution. It's very rough. And if you can imagine white noise is something like this, it doesn't have pointwise values. And I convolve it with a bump function like that, which is smooth. And after that, the disorder becomes something smooth. So it still varies, but in a smooth manner. And then it has pointwise values, and I can talk about taking its sum. And there are abstract assumptions, and our theorems can work also under abstract assumptions, some of them. Let me not go into that. And you could choose other things in this IID category. like a Poisson process, but let me not go into that. No, not all our theorems are proved for the other things, but are expected to be in some of our ideas work.
I wanted to ask, is there like a continuum picture of this? Is this like solving Poisson's equation with a random forcing or something?
Right, so in 1+1 dimension, it's the Burger's equation with the inviscid Burger's equation with kick forcing noise if you do it on the lattice. When you say continuum, do you mean that the base, instead of being ZD, becomes RD? And so when you do that, it's a question of whether it's well defined or not. No, you can definitely do that if you have a smooth disorder. So you can definitely also consider an energy, which is the integral of the norm of the gradient of phi squared, and add to that the integral of the environment at the locations where phi goes, and this could still, say x here, and this could still make sense if you do it this way. So it's definitely possible. However, the notion of an IID field will already be a little less nice because you can't make it independent between the vertices now. But you could. It wouldn't change for our results here, well, except for this IID. So we haven't done it. But more interesting would be to take a scaling limit, and that should behave differently. And it's not exactly the same as doing it on the base, which is RD. And we don't know, generally speaking, the scaling limit. Okay? So aiming to wrap up, I guess I just present you the results. I want to say something about the proof. Maybe I don't have a chance to do that. So localization and delocalization. How flat is this surface? How flat? Well, here is what we have. We may first consider the table to get an idea, and then go to the more general theorems. So we studied the height fluctuation. How far from being flat is it? And those of you who said that the surface will be power law delocalized were right in dimension 2, and also in dimension 3. But starting dimension 4, it's no longer power law delocalized. So the surfaces turn out to be power law delocalized when the base dimension is 1, 2, 3, 4, but already localized in 5 dimensions and higher. Now, those of you who are trying to compare this with the previous results on the minimal cut, the minimal cut was localized when the base dimension was 3. So we have something else going on here. Okay, I will get back to this point. Here, there is the physics numbers. So these are numerical simulations. This comes from a functional renormalization group. And everybody, also I think from functional renormalization group, or maybe some other arguments, agrees that it should be localized when the base dimension is 5 and higher. These are the rigorous bounds provided by our results. So we don't get the exponents exactly, but we have lower and upper bounds for them, which become tighter as the dimension of the base goes up. These are our results on localization and delocalization. The upper bounds are point-wise. We can bound the height at a single point. You can do even more, the maximum. And but they don't depend on n. So as you go up in codimension, the upper bound does not improve, although the physicist would tell you that higher in codimension should make the thing flatter. But our results do not reflect that. We're unable at this point. The lower bound is not a point-wise lower bound. We cannot say that at a single vertex it is fluctuative. This would be like the midpoint problem to say that a single vertex is fluctuative. But we can say that 90% of the vertices or 1% of the vertices are fluctuative. A bit weaker, but still good. And then our general lower bound, this L to the 0.6 is this L to the 3/5. For higher codimension, we can vindicate this physics prediction that the fluctuations are at least L to the 1/2. But we cannot yet resolve the open question in physics whether they're ever above 1/2. So we at least get to 1/2. For higher codimension and dimension, our bounds deteriorate, the power deteriorates, and we get this. This was called the Flory approximation in the physics literature, so we get a proof of that. And we get this log-log bound at the critical dimension 4, so we are at least able to prove that in 4 dimension, the surface delocalizes sub-power law, but we cannot show what is conjectured, that it will be log L to the power. Okay, these are our results on localization and delocalization. Another set of results that we have, which will be very quick. Sorry.
Yeah, I don't know.
Just one slide.
Yeah, okay.
Okay, sorry about that. Another set of results regards the scaling relation. As it turns out, in the physics literature, there's also a scaling relation for surfaces, not considered before by mathematicians. We're able to verify, to give rigorous versions of it. So you can ask about the energy fluctuations versus the height fluctuations. They should be related like this. Previously in our talk, we spoke about chi being 2 psi minus 1. That was really d equal 1. More generally, you have the result, the relation written here, and we have rigorous versions of it. In particular, when d equal 1 for geodesics, which was not known unconditionally before. Concurrent with our work was a work of Basu and Sly that proves it for d equal n equal 1 for rotationally invariant models under assumptions to be verified in a subsequent. But except for that, there was no unconditional proof, and that's just d equal n equal 1. So we have rigorous versions of this. Okay, so if I had more time, I would tell you something about the proofs. Basic versions of the proofs are not hard. So there are 2 slides for localization here that give some basic idea, and a main identity, which is important, and 2 but much more thick slides that say something about delocalization. So I wanted to show localization because previously I spoke about delocalization. But okay, but with this I finish, and if this wasn't so slow, it would actually move forward to open questions. Okay, thank you very much.